There we go. Can people hear me now? There we go. All right. I guess I shouldn't have messed with those settings. Okay, before we start, before I start taking questions, just a couple of things. So this morning, I did run sort of as a test, sort of a mini lesson based on today's, on the implicit differentiation, so that's lesson 5. Now there were only 4 people there. Now obviously all this stuff is not mandatory, but I just want to get a sense as to, did people just not attend because it was too early? Do you just prefer the tutorial and watching the videos on your own? So I'm just trying to get a sense, oh, I don't wake up till 11. Well, it's good to get into a routine there, folks. Okay, too early, too early. Okay. Now, the thing with the online lesson is that it's probably going to take longer than sort of a lesson that I post, but of course, you have that back and forth. So do you think that's something that people would want to try once we get into vectors, having online lessons? And again, of course, what I would do is I would, I'd post them afterwards, but it would mean that they'll likely be longer. So if I can get some feedback on that, what do we think on, okay. Okay, so maybe what we'll do is start with maybe afternoon lessons, and then we can do, you know, tutorial afterwards, or tutorial. That's it, maybe do an online lesson, and then afterwards stick around if people have questions. Okay, so I don't think I'm going to do that for lesson 6 on for this unit, because again, lesson 6 tends to be a whole bunch of different types of problems. Okay, but when we get to vectors where it's completely new material, we may start doing that. Okay, folks, it's up to you now. Questions? So at this point here, I'm hearing some background noise. I'm not hearing anybody's voice. So is it that people are not asking questions, or is there an issue with the, so remember, you can turn your speaker on and off at will. Okay, does anybody have any questions? Oh, this is going to be a short tutorial. Okay, there we go. Question 12 on page 564. All right, so let's take a look at that. So 564. All right, so here, 564, so question 12. Now, did I assign question 12? I actually don't think I assigned that one. Christina, is that just an extra one that you're doing, or? Oh, okay. I thought I had it, but well, let's do it. It's a bit of an interesting question, if I remember correctly. All right, so now, can someone tell me why? Oh, it was a homework question. Maybe that's why I'm thinking it wasn't assigned. Okay, great. So let's take a look at this here. And so can everybody see the question well? Okay, so in fact, I'll write it down here. So I'll just quickly write it down, show. All right. All right, So first of all, can somebody tell me why I need to do this using implicit differentiation? Okay, so this kind of reminds us, sort of a good reminder is when implicit differentiation is necessary as opposed to just being an option. So who wants to explain to me why I have no choice but to use implicit differentiation? Sorry, Samya, was that you? I couldn't understand what you said. Okay. Okay, so here, very good. So here it says one variable is not defined explicitly in terms of the other. So when we talk about something being defined explicitly, it means it's defined as y equals some, expression that contains only x's, okay? Now, that's not to say that implicit differentiation can't be used. So there's one of the examples, I think it was 2a, it was something like x cubed plus y cubed equals x, okay? Where here, y is defined implicitly in this equation because it's just some member, it's not isolated. Here we can isolate for y, so you can do this using traditional calculus, but in fact, it's easier algebraically to use implicit differentiation, as opposed to this example here, where as hard as you might try, you're not going to be able to isolate y in terms of x, okay? So first thing is to realize that you need to use implicit differentiation here. All right, so let's do that. So the first step of implicit differentiation is to not try to manipulate anything to solve for y, is to just take the derivative of both sides, okay? Now, when I take the derivative of the right-hand side, that's nice and easy, that's just equal to 0. What am I going to have to use here in order to find the derivative of this expression? Okay, so what derivative tools am I going to have to use here? And in fact, I see two that I'm going to have to use. So who can tell me what I'm going to have to use? Okay, there you go. So I'm going to have to first use the chain rule. Okay, but then when I find the derivative of that inside function, I'm going to have to use the quotient rule. All right, and same thing here. Okay, so let's go ahead. Now, you can sort of see that that's going to be a fairly complex expression that I'm going to get for each of those, yet the derivative is supposed to simplify to something as simple as y over x. So I'm anticipating, I actually don't remember how this problem solves, but I'm anticipating that we're going to have to do a fair bit of algebra here to get to that point. All right, so let's take the derivative of this first one. So this whole thing inside my square root, that's my u. So the derivative of u to the 1/2 is just 1/2 u to the negative 1/2, okay? And now when I take the derivative of u with respect to x, because I have a quotient, this is where I have to use the quotient rule. Okay, so I'm just going to go through my process. Derivative of the numerator is equal to 1 times the denominator function, which is just y, plus my numerator, x, times the derivative of the denominator. But this is where, at best, what I can write is the derivative of y with respect to x. Okay, now you'll notice here that I'm using prime notation instead of dy dx, and I'm just doing that just to make the writing of this a little easier. But remember what prime notation does not tell us. It doesn't specify what I'm differentiating with respect to. So you just have to remember that when you write y prime, that you remember that this represents the derivative of y with respect to x, which is what we're looking for. Okay. By the way, folks, please remember to stop me if you have a question, if you're not understanding something that I'm doing. Okay, over the denominator squared. Okay, and of course also stop me if I make, oh, thank you. Oh, there you go. Here I am telling you that. Good catch there. That should have been minus. Silly mistake on my part. Thank you. Who's that? Anna. Thank you, Anna. Okay, and now let's do the same thing with the next one. All right, so plus, now I have to find the derivative of this thing, and it's going to be almost identical. So 1/2 y over x to the negative 1/2. And then here we've got the derivative of the numerator function is going to be the derivative of y with respect to x, so y prime times the denominator function, okay, and then minus y times the derivative of the denominator function, which is just 1 all over x squared, okay? And then on the other side of the equation, derivative of 10 is just equal to 0 because it's a constant. All right. So when you take a look at this here, remember what our goal is for implicit differentiation is what's produced in taking the derivative of both sides is the exact derivative we're looking for, okay? But we're gonna have to do, some work here to make this look a little nicer. So the first thing I'm gonna do, what do you think I'm gonna do with the 1/2 here to make my life a little easier? There you go, even better than that. Not only is it common, what am I gonna do beyond that? Yeah, and once I factor, what am I gonna do once I factor? Even better than that. There you go, as I'm just gonna multiply. So in fact, what I can think of here, and normally I wouldn't write this down, is let me just start right off the bat by multiplying both sides by 2. Because when I distribute the 2 to both of these, it cancels out the 2 in the denominator, and I'm just gonna end up with 0 still in the right-hand side. Okay, so these are the kinds of things you do just to simplify your life a little bit. So let's clean this thing up here. So we've got, what do we have? We have y minus x y prime over y squared, okay, all over, what do we have here? We have square root of x over y, okay, because this goes into the denominator. Actually, I should have just written it here. I just realized that's a little stupid here. I should have written it here. Okay, and then here we have plus, what do we have here? Y prime x minus y all over this again goes into the denominator. So y over x times, what do I have? X squared. All right. So again, equal to 0. All right. So now what I have to do is I have to isolate my y prime. All right. Now, again, what is something that I can do here? We have to sort of ask ourselves if we can simplify this a little bit. Okay. Any ideas as to how we might simplify this before we move on? Okay. Common denominator. Good. Okay. So in fact, what I can do is I could just multiply both sides by the lowest common denominator, and again, get rid of, everything's gonna be multiplying to 0 on the other side, all right? So here we're gonna have to do this very carefully. So what I'm gonna do is multiply this here to that. So what do we have? We have square root of y over x times x squared times y minus xy prime. Okay, and then plus, we're going to multiply this denominator to here. So we have x over y times y squared times y prime x minus y, okay, is equal to 0. Okay. Thanks, Kieran. I got the record button on. Okay. So what can we do here now? I guess we can group together all the terms that have y prime, okay? So I'll keep everything that's got a y prime on this side. So let's see what we have. We have, looks like it's x cubed square root of y over x, okay? Don't forget the negative there, times y prime. I've also got this term here, okay, plus, well, what do I have? I have x squared y times square root of x over y times y prime. Okay, and then to the other side, okay, to the other side, I'll bring all those other terms. Okay, so I have this term here. Okay, so what do I have? I have x squared y times y over x. And this is positive, so when I bring it to the other side, it becomes negative. Okay, isn't it y squared x there? Which one is that? Let's see, so this one here is x cubed y prime, good. Here, this one is xy squared. Oh yeah, what did I write? I wrote x. There you go. Thank you very much. Yep, Samya, good job. Okay, so let me check this one again. X squared y over x, so that one looks good. And then when I take that expression, what do we have? We have, it's going to be minus, so since I'm bringing it to the other side, it's plus y cubed times x over y. Okay, all right. And so now I can factor out the y prime on this side. Okay, and then divide that to the other side. All right, so let's keep going here. So we have, I'll just flip this around so that the, I'll just flip it around so that the positive one comes first. So I've got y cubed root x over y, and then minus x squared y times y over x, okay, all over whatever's left from this one here. So again, I'll put the positive one first. So we've got x, y squared, x over y, okay, and then here minus x cubed, y over x. All right? So what we have to do now is we have to take this expression and presumably it's going to reduce to y over x, okay? Now, do we see anything here that we can do that might be of interest? Okay. Now let's remember, okay, what we're trying to show. We're trying to show that this is equal to y over x. Okay. So, any ideas here? Okay. Now, when you say factor out y over x, now why are you suggesting that here? Tell me why that's an interesting thing to do.
Because that's what we want.
Okay, and then what do we hope happens in all of this thing here?
You hope everything else equals 1.
Okay, so in other words, what we want to do is, how can you can't just, I mean, I guess you could just factor out y over x, but why is that actually a very nice thing to do? What do you notice about the numerator?
Common factor.
There you go. So you notice a common factor of y here and a common factor of x there. Okay, so let's do that. So I'm factoring out the y from the numerator, okay, and the x from the denominator. Now, is it legal for me to write it as a separate fraction? Think about it. You know, if I'm just going to write it out, so let me write it out and then you tell me if it's legal, what I just did. So I'm going to be left with y squared root x over y, okay, and then minus x squared root y over x all over, and here I'm going to be left with y squared x over y, and then here I'm going to be left with x squared y over x. Okay, so was this legal to do? Yeah, because I just factored out y from the numerator, an x from the denominator, and then I just wrote it as the product of two separate fractions. So it's legal. But not only is it legal, are we all seeing what the, you know, this is the aha moment. What is the aha moment? I want to make sure everybody sees the aha moment. There you go. I like that. It's cancel time. Oh, no difference of squares, Kieran. Much too complicated. You notice that the numerator is exactly the same as the denominator. You know, not necessarily, even from this step here, not necessarily obvious because you got so many things. Yeah, well, luckily I will ask everyone to stay here though, okay? So you notice that the numerator and denominator are exactly the same, so they reduce, and you have just y over x, okay? Now, multiply by the conjugate. I was hoping nobody was going to say that. That's what actually I was thinking somebody might say, and you know, we would have had to hopefully steer clear of that. Now, in the end, you know, obviously this question was designed so that it works out very nicely. But imagine now you've got this very complex, you know, derivative. Okay, but when you go through the whole process, it actually ends up looking very nicely. Now, I notice not tons of people watch those videos, today's lesson. So the idea is usually you try to watch the videos before you come in, but so you may or may not have seen some of the fancy stuff that comes out of these questions. But for the fun of it, let's see what this relation even looks like. Okay, so I don't know if anybody's already. So let me just actually let me use this thing here. Why is it showing me this stuff? All right, how do I get rid? Anybody know how to get rid of this on? Oh well, I'll just have to do it the old-fashioned way. So what comes first? X over y. So x divided by y. Okay. To the exponent of 1 over 2. And then plus y over x. Exponent, as you can see, I'm not quick at this here. And then equals, what was it? Equals 10. And let's see what this looks like. In fact, it's really tough to even see this here. So maybe what we'll do is we'll make this go from like negative 0.5 to 0.5. Okay. Now you'll notice here, Desmos might actually have a hard time even drawing this because it looks like there's something funny going off here. So as you can see, kind of a funny function. Okay. We'd probably have to play with the what do you call that? The X and Y axes. Yeah, so it's a hilarious function. Well, did you see any of the ones from the if you saw the ones from the worksheet, even more hilarious. All right. And in fact, if you notice number 6 on the worksheet is just go out and have fun. So once you've finished all your work, instead of watching Netflix, you can just start creating any kind of crazy functions you like. X, Y squared equals X. And there you go. And you could just spend all day creating different patterns with all these different relations that are defined implicitly. Okay. There's a couple of really nice ones on the worksheet. All right. Very nice. So again, just to kind of put things in perspective, this is the type of question which is a homework question, maybe even an assignment question. This is not the type of thing that you would expect to find on a test, okay? Even though things did work out really nicely, it may be a little more complicated than what you'd find on a test. All right, so next.
I have a question from an older lesson.
Yeah, for sure. Which one? Is it textbook or worksheet?
Textbook, page 153, number 10.
Okay, 153, number 10. 153. Okay. Okay, so the cost of producing an ordinary cylindrical tin can is determined by the materials used of the walls and the end pieces. Okay, if the end pieces are twice as expensive per square square centimeter, as the wall, find the dimensions to the nearest millimeter to make a 1,000 centimeter cube can at minimal cost. Okay, so this question here would be very similar to the question in, and assume it was in, I think it was a jewelry box question that was in the worksheet, one of the worksheets, where the cost of the sides and the cost of the top were not the same. Okay, the only thing that's different here is they don't give you a specific cost. Okay, but they do tell you that one is twice as much as the other. All right, so let's take a look at how we'd set that up. Okay, but we're going to sort of see that this is pretty similar to the one that we did. In fact, maybe a little nicer because everything's already given in terms of the same unit, centimeters. All right, so what did we say is the difference here? What is it that they don't explicitly tell me in this question compared to the one with the jewelry box? So if somebody could just chime in either, okay, they don't tell us the actual price. So before we start, if we don't know what the actual price is, well, we're gonna have to come up with some variables for that. So let me just see which one is more expensive. Tin can, the end pieces are twice as expensive as the cost for the wall. Okay, so what I'm going to do is I'm going to say let CW be the cost per square centimeter of the wall. Okay, and then C, what did they call the other one? They called it the end pieces. Okay, so CE will be the cost per square centimeter of the ends. Okay, and what do I know about CE? What can I say for sure about CE? Somebody could just chime in here, because again, we're trying to, there you go. It's 2 times whatever CW is. Okay. Now, you might sort of be wondering, how am I going to be able to actually solve this problem without knowing what these numbers are? So this is where I would tell you what I've said many times in the past is, don't worry about that yet. It's not actually a problem yet. Maybe it will be a problem, but don't let it, don't let it get you down until it actually becomes a problem. Maybe things will work out. Okay, so this is where now I'm going to go through a similar process. I'm going to say, what is it that I'm trying to, what am I trying to minimize? I'm trying to minimize the cost. And what is going to be the cost? Okay, well, it's going to be the cost to make the ends and the cost to make the wall. Okay, so again, I've got R, I've got H. Okay, now, how many ends do I have? Do they tell me if it says, well, it's a tin can. So here we're going to assume that it's a closed cylinder. Okay, it's not like it's open top. Since it's an actual can, I'm going to assume that we need both top and bottom. So what I need to do is I need to find the area of the top and bottom. Okay, so 2 times the area of the base. Okay, and then I need to multiply that by the cost per square centimeter. Okay, and the cost of the ends is CE. Okay, so times CE. Okay, and then here I'm going to add to that the area of the side, which is, the area of the side, and I have to multiply that by the cost per square centimeter of the wall. Okay, and now let's start putting in what we know. So the total cost is going to be, well, area of the base, that's just a circle. Okay, so it's going to be 2 times pi r squared times CE. But instead of writing CE, what should I be writing? What do I know about the cost of the ends? I know that it's going to be 2 times the cost of the wall. So I'm going to replace CE by 2 times CW. Okay. Now, how do I find the area of the side? Well, again, if you don't remember, you look it up and you realize that the side of the what we call the lateral area is 2 pi r. In other words, the circumference of your circle times your height, because if you sort of fold it out, it ends up becoming one big rectangle. So 2 pi r times CW. Okay, and so now what we have is we have this, sorry, 2 pi RH, forgot the H there. Okay, so I have a model with, again, this unknown cost, but I'm not going to worry about that yet. What is the thing that I need to worry about more now? What's the more worrisome thing? Who wants to chime in here? There you go. Is that the height and the radius? I've got two variables in this equation. And as before, I look to my question and I see that they give us a constraint. They tell us that the volume has to be equal to 1,000 centimeters cubed. But the volume is just pi r squared h. Okay, so I have 1,000 is equal to pi r squared h. And so I can just isolate one of these variables. I don't think you're going to be too shocked that I'm going to isolate the height, because if I can avoid bringing in any fractions or square roots, well, I can bring in a fraction, but I certainly don't want to bring in any square roots. All right, so let's clean this up here. So our model now is going to be, so 2 times 2 is 4, okay, CW. So these are just constants. Even though I don't know what the cost of the wall is, it's just a constant, okay, times r squared, or pi r squared, okay, and then plus, well, here I have 2 CW, okay, times pi times r, and h now I've rewritten as 1,000 over pi r squared. All right. And so now what did we just create? A model with only one variable. So let's again clean this up a little bit. And that r cancels out with that r. And so my final model here is going to be 4 CW pi r squared plus, and make sure I get everything here. So it looks like that's 2,000 CW over R. Okay. And what is the only restriction we really have on the R value here? Okay, because remember, anytime you give me a model, I expect to see a domain. There you go. R, well, more than can't be 0, it has to be greater than 0. R greater than 0. All right. So now, one thing here is, somebody asked me, why is it that when you have an open interval, you have to justify that it's an absolute max or min depending on when you're looking for, whereas if it's a closed interval, you don't? Well, it comes down to the fact that when you have a closed interval, you're guaranteed an absolute max and an absolute min. And you know exactly where they occur, at either the critical points or the endpoints. So you just test them all. Whatever your biggest value is, your absolute max. Whatever your minimum value is, your absolute min. Whereas when you're working with an open interval, there's no guarantee that there's an absolute max or min. So that's why you have to justify that it is one. Okay, and then from this point here, we just do what we normally do. So C prime equals, so here you have to remember that this whole thing is just a constant times the derivative of r squared. Okay, now by the way, when I write C prime, again, the problem with prime notation, remember that I'm taking the derivative with respect to the variable in my equation. So with respect to r. So the only thing I'm left with is 2r. So here I have 8 CW pi times r, okay? And now I think we've done this enough times. I'm just going to go ahead and maybe skip some steps. I know that this is 2,000 CW times, r to the negative 1. All right, so it's just going to be negative 1, so minus, and then this 2,000 CW, which is just a constant, times r to the negative 2. So that's just going to go into the denominator. Okay, and of course, what I'm actually solving for, can't you factor to make it simpler to find? Oh yeah, for sure, I could have. I mean, in the end, these were all constants. So you're correct, Ali, that I could have done some factoring first, but like I said, in the end, so it's all constants. I don't worry too much about that. So I want to make this equal to 0. Now, who can tell me why I have now solved that slight worry I had at the beginning, but I told you not to worry about, why we don't know the exact price? There you go. No, oh, more than just factor it out. There you go. Is I could just divide CW to both sides, and I realized that whatever the cost of the wall is, it's actually doesn't affect the solution to this problem. Okay. So this problem, what's nice about solving a problem like this is you're solving for whatever the original cost of the wall is. If it's $1 per square centimeter, and then the other one is 2, or it's $500 per square centimeter, and then the other one is 1,000, it doesn't matter. All we needed to know was that one was twice the cost of the other. Okay, so I can divide CW to both sides, and it just, the right-hand side is still equal, the left-hand side is still equal to 0. Okay, so let's take a look at what, I've got a couple of questions here. So Sami says, do you technically need to establish that variable? Would it be wrong to just multiply 2 pi r squared by 2? Okay, so Samia, maybe you can you explain when you create that cost function? Can you maybe speak, because I'm not understanding your question.
Yeah, I was just wondering if when you're creating that cost function, can you just multiply the 2, because we know that the end pieces are twice as expensive.
Okay, and that looks like perhaps it's similar to what Kieran is saying. So now that we've established this, you technically could. In principle, you shouldn't be assuming that the actual cost doesn't make a difference. So while I said don't worry about the fact that you didn't know about it, I don't think that I would want to assume that it doesn't make a difference until I could actually justify it. And it's really only at this point, once I see that when I'm solving the derivative equal to 0, that I could just divide both sides by CW and it doesn't affect the problem. Then at that point, you can sort of justify, oh yes, the actual value is it doesn't really matter. Sorry about that. So do you see why, it's not something I would want to assume right off the bat? Okay. It turns out it's correct, but it's something that I would prefer seeing justified in my solution. Okay. So now from there, we just, in fact, we could also divide both sides by, I'm going to assume, 2,000s divisible by 8, divided by 8. Yeah, 250. So I can even, keep going and divide both sides by 8, just get rid of it. Not necessarily, but, All right. And then here, we've done something very similar before. So I'm just going to multiply both sides of the equation by r squared. So 0 equals pi r cubed minus 250. And so r cubed is equal to 250 over pi. And so r is the cube root of 250 over pi. Okay. Now, does anybody want me to go through with this? Essentially, the next step would be, test that it indeed is an absolute minimum. Okay. So remember, you're just working from 0. This is your only critical point. So you would just show, and you would actually show it by putting it into the derivative, show that you're going from negative to positive. And then from there, it means that this local min is actually an absolute min in this interval, because it's always decreasing to the left of it, and then it's always increasing afterwards. Okay?
I have a question about that.
Yeah.
How would you justify that with words instead of like a picture? Like just a quick.
So if you wanted to justify with words, you would just essentially do what I just said. It's increasing. It's in this case here, it's a minimum, sorry. It's decreasing to cube root 250 over pi, and then increasing the rest of the interval from that number to infinity, okay? So essentially you've shown that to the left of that, it's always decreasing, and then it's always increasing. So this must be an absolute minimum. I mean, really, that's the only justification. I don't necessarily expect you to write that out in words, but that's how you would write it. It was you would just explain that from 0 to that number, it's continually decreasing, and then from that point forward, it's always increasing. Okay?
Okay.
Let's take a look. There's another question. Do you need to put 0 on the interval to explicitly show the values need to be greater than 0? Again, if you don't put it, this makes it look like it's always negative to the left of cube root of 250 over pi. Whereas I didn't check anything, because you notice that this function at 0 has a vertical asymptote. So it may have changed sign. So it's kind of good measure to show that 0 on your equation, so that you're showing that you're not saying that this function is decreasing everywhere to the left of that number, because you're not sure what's happening to the left of 0. But the problem is, not the problem, but the idea is that you don't care what's happening to the left of 0. But just for good communication, you should be clear that you're only considering this interval here, okay? Because this doesn't, you don't want this to say that the function is decreasing less than when it's less than 0, okay? So I hope you can see that most of this problem is almost identical to the jewelry box problem. The difference here is how I had to incorporate the fact that they're not giving me the actual costs. But the way that I was able to do that is write it so that only one cost value ended up being used. And in the end, because it's a constant, when you're finding the derivative, it doesn't affect, it didn't affect our solution, okay? CW could have been anything, and you would have come out to the same dimensions. Okay, any last questions on this one here? No, okay, let's go to the next question. Okay. All right, so it looks like there's no more questions. So one thing that I do want to, not so much for these, certainly not for these online tutorials, I prefer you didn't, but if you have friends at other schools that, you know, are interested in, you know, who you know are taking the course and doing the same thing that we're doing, I have no issue with you sharing my website with them if they want to, you know, keep up with some of the work, or even if they're doing things that we had already done, because not everybody necessarily follows the same order as we do. You know, you're welcome to share the resources with them. Okay, so last call for any questions either on some of this material or anything in general. All right, so do we have, do we need to have one of these things tomorrow? Yeah, no problem. So do we want to have one of these things tomorrow? Will people, okay. Yeah, so why don't we do this? Yeah, if I can just get some of these other things here. Do we want online lessons instead tomorrow? Okay. So what I'll do is I'll do the online lessons. I'll post the lessons afterwards. So I'll be posting this now that I remember to do that. Okay, so if we're going to do online lessons, though, I don't think I want to wait till 2 o'clock. Can we please do that at, oh no, wait a minute. I got to check. I have a bunch of meetings tomorrow. This is my third meeting today. 10, 11, 12. Actually, you know what, folks? Can we please do 2 o'clock? Because I have a meeting at noon and I don't know how long that's going to last. So we're going to do 2 o'clock. What I'll do is I already had the videos for the last 2 questions from lesson 6. So I'm going to leave those. I won't do those 2 questions, but I'll do the first 4 questions. And by the way, if you want to even let your friends know, what we're going to do tomorrow other than finding maxima and minima using derivatives, is probably one of the most important applications that you're going to see from this course, that shows up in a lot of things: physics, chemistry, probably even biology. Okay, so tomorrow's lesson, I'll be honest with you, is technically not in our curriculum, but I got to say it's insane not to do it because it's such an important topic. Okay, so again, 2 p.m. tomorrow. There's still a few of your friends that I haven't heard of, so if you know that maybe a couple of people need a little push and you think it might be a good idea for them to do a little bit more work, please, encourage them to participate. Okay, so if there's no further questions, we're gonna shut this down. Okay.
Thank you.
Yeah, no, my pleasure. So we'll see you. We'll see you tomorrow. We'll see you tomorrow at 2 o'clock. Thank you, thank you, thank you. Yeah, bye, 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 everybody. Okay, enjoy the rest of the day.